We're finally here at Boston Dynamics.
Everything seems to be in order. Welcome.
All right, let's take a look inside this incredible facility.
Rerouting power to the auxiliary servos.
Confirmed. The energy signature is holding steady.
A precision hydraulic components manufacturer. High-pressure hydraulic cylinders, valves, and manifolds.
Precision sensor manufacturers. LiDAR units, stereo vision cameras, IMUs, force torque sensors.
The onboard computing systems that run Boston Dynamics locomotion algorithms, processing sensor data and generating motor commands faster than any human reflex.
From the cluttered labs of MIT to the proving ground of the DARPA challenge, the goal was always clear: build machines that could...
The force output is stable at 200 newtons.
And the sensor alignment looks perfect on the tablet. How are the stress tests looking on the actuator?
We're seeing consistent performance up to the limit.
Run the diagnostic sweep on the knee.
Getting consistent torque readings across the full articulation. Clear.
Good.
Initiate shoulder rotation sequence alpha.
Actuator response nominal. Sensor readings stable.
Confirmed. We have a successful upright stance.
How are the balance metrics reacting to the incline?
Minimal deviation. The adjustments to the ankle servos seem effective.
Capability validation sequence engaged. Stair climbing, rough terrain navigation, and successful payload handling confirmed. All specifications met.
This agreement covers our unreleased robot designs and ongoing development programs. Please review Section 3 carefully before signing.
The torque on the left hip is stabilizing.
Solid recovery at maximum displacement. Data logged.
Machines that were never sold, but that produced the understanding that made sold products possible.
Is there a capability in current Boston Dynamics robots that the public has not yet seen demonstrated?
This graph confirms their approach to the inverse kinematics.
Right, and the patent filing details the joint limits.
That explains the increased range of motion we observed.
Yeah.
As the leg makes contact, they analyze these force vectors. The real challenge.
We're studying how the brain coordinates movement, specifically the neural pathways involved in walking. It's complex, but the progress is encouraging.
The fatigue life prediction just dropped significantly. See that transition?
Yes, the thermal variance is causing premature failure. We need to adjust the load sequence.
The adrenaline sensor. The inertial certainly show the moment it lost traction.
But the gate adjustment valve compensated within milliseconds.
Check the integrity of the rear seals now. Focus on the power input.
Looks good. The water is channeling away as expected.
The actuators on the right knee are spiking past tolerance.
I see it. Rerouting power to the cooling systems now.
Archive documentation of a joint bearing failure mode discovered in early spot production. A fatigue failure appearing on
The revised bearing surface finish specification and the enhanced accelerated fatigue testing protocol implemented after the early spot production event.
The balance metrics are well within specification, even with the arm extended.
Performance confirmed. Let's log the results. If we adjust the tolerance here, we could reduce the heat signature.
The simulation shows that stabilizes the gate, but we'll need to rewrite the inverse kinematics.
Get a closer look at that timer.
Copy that, moving the arm in slowly.
If we reroute the power flow here, the servo response time improves significantly.
That explains the bottleneck we saw in the simulations.
Look at the inverse kinematics data here. Joint 2 is exceeding the threshold.
Yes, but the manipulation success rate is holding at 95%.
Our environmental management programs focus on energy use tracking, material waste reduction, and component lifecycle management.
The update is pushing through.
We have stable telemetry. The servos are responding well.
The robot takes care of the dangerous tasks now. We no longer perform confined space entries,
climb the towers, or walk the active areas during maintenance.
If we optimize the inverse dynamics here, it should handle the terrain better.
Okay, deploying the update, much better stabilization on that step.
The Atlas unit handled the structural collapse autonomously.
And the spots have already mapped the safest entry points for the crew.
Whoa! You almost interfered with the test, didn't you?
It was a reflex.
Look at this old photo. Three-way locomotion study. 2 passed. Classic.
Mummy, did you build any new robots today?
I am working on one.
What will it be able to do?
Update stabilized the gate. We clocked almost double the uptime.
Yeah, but look at how it handles that cornering routine. Still some drift.
True, we almost lost it.
He joined Boston Dynamics when the most advanced robot was hydraulically powered, GPS navigated, and could barely walk on flat ground.
The SLAM data from the tunnel run looks solid.
Yeah, Spot handled the water levels better than expected.
We should implement that trajectory optimization on Atlas too.
When the Atlas fell, the damage was significant. We realized then that we had to fundamentally rethink how we approach fall recovery.
We're confirming the calibration here. The mechanical reasoning is ensuring zero backlash before the routine begins. Watch the servo response now.
Got it. What's the acceptable deviation?
The acceptance record is signed. Congratulations on passing all phases.
Thank you. We are ready for deployment.
I didn't set a return trigger for this sequence.
Neither did I.
Neither did I.
It just decided to go home.
This is where innovation happens. The automated systems you see here are streamlining our testing process, allowing us to accelerate development like never before.
Quick flashes, a completely different kind of manufacturing environment. Ancient craft, modern precision, a product made by humans for thousands of years.
Footage not shown in this episode 40. The extended Atlas Development Lab corridor, the complete prototype.